Tonight, something outran the stars over Mars. October 2nd, 2025. Just after midnight, the Perseverance rover's night sky camera caught a flash, thin as a strand of light, racing across the Martian constellations at nearly 60 kilometers per second. Within hours, the clip vanished from public servers. Mars orbiters went silent, and then a faint green flash appeared in a handful of reconstructed frames before the entire sequence was pulled for review. NASA has not released an official statement. The European Space Agency has declined to comment. But amateur astronomers who downloaded the raw Perseverance data before it disappeared are saying the same thing. The streak's timing and trajectory match the interstellar visitor known as 3I Atlas, the same object that brushed past Mars this week on its one-way path through the solar system. So, what did the first flyby images actually capture? A dust fragment glowing in the sun? Or something no comet should ever do? As the official feeds remain dark, scientists and the public are left with one haunting question. What happened in those missing frames? And why does the world's most advanced space agency seem so hesitant to show them? At first, it seemed like a glitch, another cosmic ray hit, a random artifact in Perseverance's sky monitor. Mars has plenty of those. Its thin atmosphere allows high-energy particles to streak straight into the camera sensor, painting brief lines that vanish with the next frame. But this time, the streak didn't vanish. A name began trending across astronomy forums within hours. Stephen Burns, a veteran amateur from Colorado Springs, known for dissecting rover data. He was among the first to comb through Perseverance's open raw archive from Sol 1476, the night of October 2nd. Using precise starfield calibration, he aligned each frame with a fixed celestial grid, accounting for the rover's camera tilt and Mars's slow rotation. And there it was again, a razor-thin streak crossing 37 frames in sequence, moving at a steady 60 kilometers per second. That number didn't belong to anything local. Meteors in Mars's sky rarely exceed 15 kilometers s. Satellites orbit far slower. Even cosmic rays, when stacked frame by frame, never trace a continuous, consistent line across multiple exposures. Burns double-checked timestamps, compared plate scales using known star separations, and uploaded his analysis in a 9-minute time-lapse video titled "The Visitor over Jezero." By morning, the footage had gone viral. Tens of thousands downloaded the same frames and tried to replicate his process. Some saw nothing but noise. Others found the same luminous trail, perfectly matching the predicted motion of 3I Atlas from JPL Horizons. The debate exploded. Was Burns chasing artifacts, or had he stumbled upon the first interstellar object ever recorded from the surface of another planet? Hours later, something stranger happened. A handful of users noticed a brief green flare at the start of the streak, just 2 frames long, subtle but unmistakable. And yet, when they returned to NASA's site, the original raw directory had been locked. No public notice, no mirrors, only cached copies remained. For many, it was just routine data maintenance. For others, it was the first sign that something about 3I Atlas's Mars flyby didn't fit the standard script. A mystery had begun, and the next images from orbit would either dissolve the illusion or confirm that something genuinely impossible had just flown past Mars. Within a single day, every corner of the astronomical internet lit up. On Reddit, cloudy nights, and NASA's own open data threads, the phrase "Burns streak" became shorthand for both curiosity and controversy. By then, over 400 independent analysts had downloaded the same Perseverance frames, running them through their own pipelines in MATLAB, Python, and PixInsight. Some succeeded in rebuilding the faint line. Others swore it was nothing but stacked noise enhanced by wishful eyes. A few claimed to detect secondary flashes, smaller and faster, offset from the main track by a fraction of a degree. That suggestion, that there could be multiple fast movers, ignited chaos. If true, the object wasn't alone. Debate quickly divided into camps. On one side were the realists, scientists insisting it was a cosmic ray streak or a satellite glint from the Mars orbiters themselves. On the other side stood the pattern hunters, cross-referencing every known Mars satellite trajectory, every dust event, every camera artifact cataloged since landing. None matched the geometry or persistence of Burns' streak. At the center of it all was the green flash, those two enigmatic frames at Zuzif Ozo 3 UTC. When one team decomposed the color channels, the anomaly concentrated entirely in the green band near 520 nanometers, with a brightness spike 8 times the local background. It looked like the spectral signature of dicarbon, the C2 molecule that gives comets their emerald glow when sunlight splits their bonds. But that created a paradox. Every early spectral estimate of 3I Atlas suggested it lacked C2 entirely. How could a comet shine in green without the very compound that makes comets green? NASA remained silent. ESA offered a single line in a press bulletin. Data from Mars-based assets are under calibration review. That was it. No confirmation, no denial. For data-hungry scientists, it was the equivalent of closing the blinds during a fireworks show. Then came the orbiters, the true eyes of the operation. 3 spacecraft had been scheduled to capture the flyby. The Mars Reconnaissance Orbiter, with its high-rise camera capable of sub-meter resolution on the surface, but nearly blind to fast-moving distant targets. ExoMars Trace Gas Orbiter, carrying the color imager Cassis, reprogrammed to snap rapid 4-band sequences along the predicted trajectory. And Mars Express, whose HRSC and high-resolution SRC lenses could sweep broad swaths of sky to search for diffuse jets or multiple nuclei. The imaging plan was a ballet of timing and geometry. Each orbiter had to slew off its normal nadir pointing, predict the comet's position hours ahead, and shoot into deep space with only a few seconds of exposure margin. One error in the ephemeris, and 3I Atlas would never cross the frame. As the flyby window opened, signals streamed back through the deep space network, then went dark. No preview frames, no quick-look images. In most missions, at least uncalibrated shots appear within days. This time, nothing. Inside JPL, according to one engineer who spoke anonymously to Sky Monitor Weekly, teams were cautious beyond precedent. For moving targets, standard cosmic ray rejection filters can erase genuine streaks. Stack images too aggressively, and real fragments vanish. Too lightly, and false streaks multiply. No one wanted to release a frame that could spark global hysteria if misinterpreted. Meanwhile, the amateur community kept digging. Some cross-checked the timing of the Perseverance streak against the known orientation of Mars itself, and found that the trajectory lined up perfectly with this 3I Atlas's predicted sky path at that very minute. That alignment, within less than 1/10 of a degree, was statistically extraordinary. By October 4th, the story reached mainstream outlets. Headlines screamed, "Interstellar object captured from Mars, NASA quiet." Talk shows speculated about alien probes. Scientists urged patience, yet the silence only deepened the suspense. Every new thread circled back to one haunting contradiction: a comet glowing green without C2, streaking across the Martian sky at 60 kilometers per second, and leaving behind missing data that no one could see. Something had happened that night over Jezero Crater. The only question left was whether the orbiters, those billion-dollar witnesses circling Mars, had caught it too. For a few hours on October 3rd, Mars became the best vantage point in the entire solar system. Earth was blinded by the sun's glare. Our telescopes couldn't even turn toward the event without risking their optics. That left 3 orbiters racing above the red planet as the only witnesses to 3I Atlas's historic flyby. At Mission Control in Pasadena, the schedule read like a heartbeat. 0.12. UTC, Mars Reconnaissance Orbiter, slews 5 degrees off nadir. High rise is configured for deep sky capture, a setting it was never meant to use. 0.17 UTC, ExoMars Trace. Gas orbiter begins Cassis exposure sequence, 4 color bands, 10-second intervals. 0.23 UTC, Mars Express activates HRSC stereo channels and high-resolution SRC imager, scanning the predicted path. Each shot is a calculated gamble. If the prediction is late by even 1 second, the object will already have crossed out of frame. If early, the cameras stare into empty sky. Engineers at JPL call it shooting at a bullet with another bullet. HiRISE was designed to photograph Martian dunes and boulders just 30 kilometers below its orbit, not to chase an object millions of kilometers away. Still, the team hoped that by stacking dozens of ultra-short exposures, they might pick up a faint, elongated blur moving against the background stars. Cassie's, on the other hand, offered color sensitivity and was best suited to detect any jets or chemical emissions. Mars Express, with its wide sweep, was there to catch anything that moved outside the other camera's narrow fields. From the outside, the operation looked routine, but inside JPL, tension was mounting. The imaging leads knew that 3I Atlas wasn't behaving like a normal comet. Its outgassing seemed inverted, jets pointed sunward instead of away, and its rotation rate suggested enormous mass. That meant that any visible structure, fragments, flashes, or chemical plumes could rewrite entire chapters of cometary physics. When the flyby window closed, telemetry showed that all 3 spacecraft had captured data. But instead of celebration, the teams went silent. Usually, at least one quick-look mosaic appears within days, even before full calibration. This time, the raw archives stayed blank. The only updates came from terse internal logs marked pending radiometric correction and ephemeris cross-verification in progress. By October 5th, no image had surfaced. Independent researchers checked the planetary data system. Nothing. The ESA-PSA archive, empty. No thumbnails, no metadata. For an event this public, that was unheard of. Behind the scenes, the explanation was less conspiratorial and more terrifyingly complex. Moving target campaigns break the standard pipelines. Calibration tools tuned for stationary Martian terrain don't know how to handle a streaking target that shifts by dozens of pixels between frames. Cosmic ray rejection algorithms might misread genuine light curves as noise. One imaging. Specialists later explained anonymously, for something like this, every single pixel matters. One misalignment, one cosmic ray spike, and you'll invent fragments that don't exist, or erase the ones that do. Inside the Mars Imaging and Calibration Lab, scientists were manually cross-checking every frame against predicted motion curves from JPL horizons. That's the same system used to plot planetary ephemerides to within arc-seconds of precision. Each anomaly had to be flagged, reviewed, and verified before public release. Still, the longer the silence stretched, the louder the questions grew. What could possibly take so long? Had the cameras missed the target entirely, or was there something in those images, something odd enough, that required a deeper look before the world saw it? On astronomy forums, one line kept echoing: "No raw images." The phrase became a rallying cry, a symbol of both frustration and fascination. To the cautious, it was a sign of scientific integrity. To the skeptics, it sounded like censorship. By week's end, rumors spread that internal calibration teams had flagged several frames showing unexpected geometric streaks, parallel, evenly spaced, and consistent across multiple sensors. Whether those were cosmic rays, fragments, or something else entirely, no one outside the control rooms could know. But one fact remained undeniable. In that brief hour above Mars, every eye humanity had, beyond Earth, turned toward the same mysterious traveler. And for reasons no one could yet explain, the first images of that encounter had simply disappeared. In science, when direct evidence goes missing, imagination fills the void, but not without rules. The researchers and the public began sketching out 3 competing explanations for what those lost frames might contain. Each one felt plausible in its own way. Each one carried its own implications, some routine, some extraordinary. Scenario 1. The natural explanation. The simplest answer is usually the right one. In this version, the green flash was nothing more than a transient optical illusion, a trick of light amplified by stacking noisy images. Mars's thin atmosphere scatters solar particles differently than Earth's, and Perseverance's sky camera isn't designed for low-light color calibration. A random cosmic ray hit could register as a bright green spike, while frame-to-frame alignment errors stretched it into a moving streak. In this model, 3I Atlas is simply a massive, volatile comet, larger and denser than expected, rich in carbon dioxide, but poor in water and dicarbon. Its forward-pointing jet isn't alien, merely a side effect of complex gas pressure as it rotated through solar wind. A beautiful fluke, not a mystery. If the delayed images ever appear, this scenario predicts we'll see nothing unusual at all, just a faint blur, perhaps a fragmenting coma illuminated by sunlight, and nothing that would rewrite textbooks. But not everyone was satisfied. Scenario 2, the catastrophic event. Others proposed that something dramatic had occurred during the Mars flyby itself. The missing frames, they argued, might hide a fragmentation event, a breakup triggered by thermal stress or rotational instability. The green flash could be the instantaneous release of volatile gases as internal pressure bursts through the crust, producing a brief, luminous emission. Supporting this idea, several orbital simulations showed that 3I Atlas had passed close enough to Mars to experience a mild gravitational flex, potentially enough to destabilize an already fragile nucleus. If true, fragments could have scattered across tens of thousands of kilometers, some possibly bright enough to register as secondary streaks in the Perseverance data. NASA has seen this pattern before. Comet C 2019 Y4, also nicknamed Atlas, shattered spectacularly near the Sun in 2020, producing a cloud of fragments that mimicked coordinated motion. To skeptics, the new 3I Atlas might just be another casualty of the same family line. Still, the coincidence was uncanny. Both objects named Atlas, both disintegrating unexpectedly, both leaving scientists scrambling for answers. Yet even the breakup theory failed to explain one detail. Why was there no measurable change in trajectory? 3I Atlas's path remained eerily smooth, showing almost no non-gravitational acceleration. A true fragmentation should have nudged it ever so slightly, but this object moved as if anchored by something far denser, something solid, not brittle ice. Scenario 3, the unthinkable. And then came the theory that no official scientist wanted to touch. What if 3I Atlas isn't behaving like a comet because it isn't one? Astrophysicist Loeb, known for his bold takes on interstellar phenomena, published a short preprint that poured gasoline on the debate. His team had run Monte Carlo simulations tracing the object's path backward through the galaxy. Their results suggested that, by pure geometry, 3I Atlas's trajectory intersected the sky coordinates of the 1977 WOW radio signal, the famous 72-second narrowband burst at 1420 MHz. The hydrogen line long considered the prime candidate frequency for interstellar communication. The chance of overlap? Roughly 0.6%. Low, but not impossible. Loeb's group stopped short of claiming causality, but their message was clear. If you're going to search for engineered artifacts, start with the objects that break natural laws. Those that glow green without the right molecules, shed no measurable thrust, and hold their course through solar turbulence as if guided. Mainstream researchers push back hard. They warn that positional coincidence doesn't imply connection, and that radio data from 1977 had huge uncertainties. The hydrogen line, after all, is a natural emission of neutral hydrogen clouds, not an alien beacon. Still, the seed of doubt had been planted. And as the silence from NASA dragged on, the line between skepticism and possibility began to blur. If the lost frames reveal nothing unusual, science will move on. But if they show structured geometry, parallel streaks, synchronized flashes, or anything that repeats, the implications would reach far beyond cometary physics. It would mean that somewhere, out there between the stars, a piece of engineered material crossed into our solar system, swept past Mars, and left before we even knew what questions to ask. For now, all anyone can do is wait. The next observation window will open once 3I Atlas re-emerges from behind the Sun in early December. Until then, every scientist, skeptic, and dreamer must wrestle with the same unsettling thought. Maybe the universe just gave us a signal, and we blinked. By mid-October, silence had hardened into suspense. No new images, no spectra, no official word. The global conversation about 3I to Atlas began to shift, from curiosity about a flyby to anxiety about what the event might mean. The object had brushed Mars and vanished into sunlight, but its shadow now stretched across policy meetings, research budgets, even philosophy classrooms. The first consequence was scientific. Every model of interstellar debris now looks suspect. If 3I Atlas truly possessed the density implied by its unperturbed path, then the equations that predict outgassing, jet momentum, and mass distribution all break down. Planetary scientists quietly began rewriting simulation code, building non-volatile templates for objects that behave like metal rather than ice. Some called it the birth of a new discipline, interstellar materials science. Then came the bureaucratic fallout. Inside NASA, a debate flared between transparency and caution. Should raw data be dumped publicly, even if unverified, or withheld until every cosmic ray artifact was ruled out? The decision mattered more than reputation. It touched the core of scientific ethics. In an era of instant virality, a single misinterpreted pixel could fuel global conspiracy. Yet, withholding data only feeds that same fire. The question grew philosophical. Who owns truth once it leaves Earth? Beyond the agencies, the implications reached academia and faith alike. If 3I Atlas were simply a massive, anomalous comet, it would still teach humility. The universe produces structures far beyond our prediction. But if even one clue hinted at deliberate engineering, every assumption about our cosmic solitude would collapse. Bioethicists and theologians met with astrobiologists to discuss contingency plans long written but never used, protocols for first contact without contact. The public reaction told its own story. For millions, this wasn't about chemistry or orbital mechanics. It was about identity. The idea that something built, however ancient, however silent, had just swept through our solar system shook the comfortable narrative that humanity stands alone as the maker of machines. For others, the mystery only reinforced faith itself. Evidence, perhaps, that creation is wider and stranger than doctrine ever dared to imagine. Meanwhile, engineers looked ahead. If an interstellar object can glide through the inner system once every few years, then future missions could be designed to intercept one deliberately. Concepts like Comet Interceptor 2 or Atlas Tracker began appearing in proposal drafts. Autonomous probes waiting in solar orbit, ready to sprint toward the next unknown visitor. Each design carried a quiet urgency. Next time, don't miss the shot. Even politics found a way in. Lawmakers asked who would control the next data stream, NASA, ESA, or an international body. Some argued for an open sky treaty, ensuring that no single nation could classify the extraterrestrial evidence. Others insisted on national security oversight, just in case artificial meant technologically advanced. In hearings, scientists tried to keep the focus on physics, not fear. But beneath the policy debates and the spreadsheets, a subtler change was unfolding. For the first time in decades, the scientific world was united not by certainty, but by wonder. Graduate students pulled all-nighters rerunning spectral models. Veteran astronomers logged into forums once dismissed as fringe. Everyone, from amateurs with backyard telescopes to mission directors at JPL, waited for the same thing: a signal, an update, a single unambiguous frame. Whatever the truth of 3I Atlas turns out to be, its legacy is already here, a reminder that knowledge can vanish as quickly as a streak across a Martian sky, and that our understanding of the cosmos remains as fragile as the data we trust to explain it. Beneath the headlines and speculation, the story of 3I Atlas is also the story of people, the sleepless, unseen humans behind every byte of data and every blurred frame. Inside mission control rooms across 2 continents, engineers who had once mapped dunes and dust storms suddenly found themselves aiming cameras at the impossible. At the Mars Reconnaissance Orbiter Operations Center in Pasadena, one technician later recalled the silence of that night. The air thick with the hum of monitors, the clock ticking through every second of exposure. They had prepared for weeks, recalibrating HiRISE to follow a target it could barely see, updating software that was never meant to track something moving that fast. When the final sequence uploaded, there were no cheers, only a long exhale, followed by the low murmur of telemetry decoding. "If it's there," someone whispered, "we'll find it." Meanwhile, halfway across the world, in a small observatory outside Pune, India, amateur astronomer Priya Raalo sat in darkness, her laptop glowing with downloaded Perseverance frames. She wasn't chasing fame. She was chasing truth, the faint hope that her home process stack might show what the official data hadn't. At 2 in the morning, she saw it, a thin, almost imperceptible slash of light tracing across the Martian star field. "For a second," she said later, "I felt like I was standing on Mars myself." Online, thousands of others followed suit. They weren't professionals, but coders, teachers, hobbyists, ordinary people running Python scripts and posting graphs into open forums. Some debated filter wavelengths. Others wrote software to simulate Mars's atmospheric scattering. What united them wasn't expertise but devotion. A global network of volunteers refusing to let silence be the final word. And inside NASA's Jet Propulsion Laboratory, a young imaging analyst named Eli Carter became the reluctant face of caution. He was tasked with validating every suspected anomaly before public release. Each streak, each flare, had to be examined under multiple calibrations. For 2 weeks straight, he barely slept, eating from vending machines and double-checking frame alignments until his eyes ached. When asked what kept him going, he said simply, "We owe it to history to be right, not first." Their efforts, from backyard observatories to billion-dollar spacecraft, converge into the same quiet truth. Discovery is never instant. It's built on obsession, patience, and the courage to confront the unknown, pixel by pixel. Tonight, as the world still waits for official confirmation, these are the people keeping watch, the ones staring into the digital void, hoping the next image upload will finally answer the question that keeps them awake. What really passed in front of Mars that night? And what, if anything, was looking back? Morning returns to Mars in silence. The dust settles. The orbiters glide on, still transmitting telemetry that the public cannot yet see. Somewhere inside a JPL server farm, millions of pixels sit locked behind review gates, a digital vault of unanswered questions. Across Earth, humanity wakes to the same mystery. What exactly did those cameras capture? A fragment of ice? A burst of gas? Or something that refuses to fit inside any equation we've written so far? By now, 3i Atlas has slipped behind the sun, invisible, untouchable, drifting back toward the dark between the stars. It will re-emerge in December when the geometry of the orbit shifts again, and the world will look once more. Maybe we'll see a simple smudge, fading as it escapes our system. Maybe we'll see nothing at all. But maybe, just maybe, we'll find that the questions it left behind matter more than any image ever could. In every age, discovery begins with disbelief. Galileo's moons of Jupiter, Einstein's bending of light, Voyager's pale blue dot, and now, perhaps, the faint green shimmer over Jezero. Whether 3i Atlas is stone, ice, or something engineered, it has already changed us. It reminded scientists why they started looking up, reminded skeptics that mystery still breathes between the data points, and reminded dreamers that the unknown is not a threat, it's an invitation. Because in the end, the greatest shock may not come from what NASA finds in those missing frames. It may come from realizing how much of the universe still lies beyond the edges of our certainty, and how small, yet astonishingly curious, we are within it. So until the next signal, the next flash, the next interstellar wanderer, we wait and we listen. Because somewhere out there, in the quiet between the planets, a story continues to unfold, one that began with a green flash over Mars and ends for now in wonder.